Hello there! This is Dr. B giving you an additional example problem for the t-test single sample using raw data. So in Dr. Marshall's example video, she gave you the standard deviation and the sample mean, but in this video, I'm going to remind you of how to calculate those things for yourself. So remember, for the t-test for single samples, you base your standard error on the sample standard deviation because you don't know what the population standard deviation is. So sometimes you may be required to actually calculate the sample standard deviation to do those computations. So I just wanted to give you a refresher on how to do that, and also how to state the hypothesis in symbols, and how to use the standard deviation to calculate the standard error instead of the variance, which you can use the standard deviation or the variance to calculate the standard error. It doesn't matter. Dr. Marshall showed you how to use the variance. I'm going to show you how to use the standard deviation just so you can choose which way you would like to do it. All right, so let's go ahead and look at this hypothesis test. It's very similar to the video that Dr. Marshall posted, but now instead of having a big sample, we have a small sample of 10 men, and we're using raw data to figure out the t-statistic instead of just having the values provided. So based on this sample of 10 men older than 35 who exercise regularly, does it appear that American men older than 35 get significantly better sleep if they exercise regularly? And if so, what is the size of the effect? So just like the previous example problem, sleep quality ratings were measured on a scale from 1, terrible sleep quality, to 7, the best sleep quality possible. And so we want to see if, based on this sample of only 10, do we think that every man who exercises regularly is going to get better sleep? It's the heart of inferential statistics. So let's start with step 1, where we're going to state the hypothesis, but I'm going to state this in symbols instead of words. So for our alternative hypothesis, what we expect to see, if we are expecting better sleep, right? Then we have a one-tailed test, and we think that the population mean implied by our sample, right? If the entire population got more exercise based on this sample, if we reject the null, then we think that that mean would be greater than the population mean of 4. So let's put that up here. So in the previous example that you watched, Dr. Marshall's example, the population mean was stated to be 4. I'll keep it the same way here. So if it's not greater than 4, then your null would say, well, if they're not getting significantly better sleep, then they're either getting significantly worse sleep or their sleep quality hasn't really changed. So that would be your null hypothesis in symbols. Then for step 2, you need to find t-crit. Now remember, unlike the z-test, you have to consider the sample size when you look for your values of t-crit. And that's what gets at this thing called DF, or degrees of freedom, which for this type of t-test, a t-test for a single sample, degrees of freedom is equal to the sample size minus 1. So what's our sample size? It's 10. You also know it's 10 if you add 1 plus 4 is 5, plus 2 is 7, plus 3 is 10, right? If you add these up, you get the sum of f, which is equal to the sample size. So to find degrees of freedom, we take 10 minus 1, and we get 9. Now you also need to consider what's your alpha level, and is it a 1 or a 2-tailed test? So in this case, our alpha level is 0.05, so I'm just going to jot that down. And I already identified that we have a one-tailed test, and we're only looking for values on the high end, or on the right side of the distribution, right? Because we're looking for better sleep, higher scores in our sample. So now let's go to our t-distribution, look for degrees of freedom of 9, alpha level 0.05, one-tailed test. So here's our t-distribution. We look for degrees of freedom 9, and we're looking at a one-tailed test with an alpha level of 0.05. So this is the only column that we're interested in, right? One-tailed test, alpha level 0.05. We go down and we see where that matches up with our 9. And I'm looking right here. So 9, boom, one tail, 0.05 is our alpha level. So 1.833 is the critical value for this test. 1.833. So if we drew out our critical region, it would kind of look like this. So in the middle would be our population mean of 4. We don't know what our sample mean is yet. Let's see. So let's write M and Z. The Z-score for our population mean is 0, as always. And now our T-crit is 1.833. So if we calculate a t-statistic in step 3 that is 1.833 or higher, then we can reject the null hypothesis in support of the alternative hypothesis that states that, yeah, if you exercise regularly and you're a male over 35, you're going to get better sleep quality than if you didn't. If we calculate the, I put a Z there, I'm still in Z mode, T, right? We don't know the population standard deviation, so we can't calculate Z. This is a T. And just like Z, the population mean has a T value of 0. So if we calculate our t-statistic in step 3 for our sample, and we get a value that's less than 1.833, then we have failed to reject the null, which says that either sleep quality is worse or it's not really any different based on exercise. So now let's do some serious calculations. All right, so I did some pre-calculations for you on the screen here. This is the original data, right? Sleep quality ratings. 1 man said that he had a 7 for sleep quality. 4 men said they have a 6 for sleep quality, so on and so forth. These are the preliminary calculations that you need to calculate all the values that lead up to the t-statistic. So the first thing that we want to look at is I know that at some point I'm going to need my sum of x to calculate my sample mean. So if I take each x times each f, 7 times 1 is 7, 6 times 4 is 24, all the way down, add those together, and I get my sum of x, which is equal to 53. Now to get my sum of x squared, right, if I squared each score and added it together, instead of writing 7 once and 6 4 times and 5 twice and 4 3 times and then squaring them and adding them together, I can shorten that process by using my table. First thing I need to do is take my each x and square it. So 7 times 7, 6 times 6, 5 times 5, 4 times 4, so on and so forth. If I added those numbers together, that would be just as meaningless as if I added these numbers together, right? Because that does not tell you really anything, because it doesn't take into account that we have 1 7 and 4 6s and 2 5s and 3 4s. So what I need to do is take each one of those squared x's and multiply it by the frequency. So we have 49 times 1 and 36 times 4, this times this, right? And so on and so forth. That's where those numbers come from. Then we add those together, and we have sum of x squared of 291. These numbers are going to be really useful for our mean, right here, and for our sum of squares, right? So kind of a process. When you start to get into these formulas that build upon previous formulas, I usually start by writing off my final formula that I'm going to need, right? So the final value that I'm going to calculate is my t-statistic. And I know that the formula for t is equal to the sample mean minus the population mean divided by the estimated standard error based on my sample standard deviation. Now at this point, the only value that I know is my population mean. I don't know these other values, so I need to write down some additional formulas. So let's go ahead and start with the sample mean. So the sample mean is equal to the sum of x divided by n. Or in other words, if you add all the scores together and then divide by the total number of scores. So this would be 53 divided by 1 plus 4 plus 2 plus 3, n equals 10. So my sample mean is 5.3. So now I can go back up to my t formula and get rid of this little question mark and fill it in with a 5.3. And so I know that my sample mean is 1.3 points higher than my population mean. But at this point, that's not enough proof for me to say that, yeah, my sample mean is significantly higher than my population mean, or I think that all men who get more exercise are going to have better sleep quality based on the sample. We have to compare that observed difference to the difference we would expect to see just due to chance, even if exercise had no impact on sleep quality. In other words, we need to compare that to our standard error, or our estimated standard error. So I'm going to go ahead and write down my standard error formula. And my standard error formula is, the one I'm going to use, is the standard deviation divided by the square root of the sample size. You could also use this version of the standard error formula. You'll get the same exact value. It doesn't matter which one you use. All right, so I'm looking at this and I'm like, okay, well, I don't know what S is, right? I don't know that. I don't know what my standard deviation is yet. I haven't calculated it, but I do know that my sample size is 10, so I can just fill that in. Kind of the same thing here, right? I don't know my variance, but I do know that my sample size is 10. All right, so I'm going to go ahead and delete that because we're going to fill that in with a number. So now I'm looking at this and I need to know what S is. I need to know my standard deviation. So I'll write down that formula. And the formula for the standard deviation is the square root of the sum of squares divided by n minus 1, right? Because it's a sample. So be careful when you write your standard deviation formula for your sample that you put n minus 1 in the denominator, not just n. So I'm looking at this, and we'll calculate the variance along the way, so I can plug that into this version of the formula. Just, remember the variance is what you get inside of the square root before you take the square root to get the standard deviation. So I'll rewrite this as, I don't know what in the numerator, divided by my sample size minus 1. So what is this blank? It's SS, right? My sum of squares. I don't know what that is yet. So I'll write down that formula. And luckily, I had the foresight to make those calculations that I needed for sum of squares, right? Using these values here. So if I take each x value and square and add it together, I already found that to be 291. And then remember, when you're doing your sum of squares formula, this second piece of the formula looks really similar to what we did for our mean. There's just a square in the numerator. So my sum of x, I already found that to be 53. We're going to square that, divide by my sample size of 10. Okay, so this becomes, one step at a time, 291 minus, I'm going to solve for my exponent, 53 squared becomes 2,809 divided by 10. Now I'm going to solve for my division, and I'm left with 291 minus 280.9. And my sum of squares is 10.1. I'm going to go ahead and underline that because I need that for this next formula, right? So now I'm working my way up. I finally have everything I need to calculate my standard deviation. So I'll plug 10.1 in here. And this becomes the square root of, I need to solve for that subtraction in the denominator before I can do anything else. So 10.1 divided by 9 equals the square root of 1.122. What is 1.122? That would be my variance, right? I calculated on my way to getting my standard deviation, which is equal to 1.059. So I drew two versions of the standard error formula, and I'll show you how you can do both. But first things first, let's just talk a little bit about what the standard deviation tells me. So this 1.059, this tells me that on average, scores in my sample, so these guys right here, right? The scores in my sample tend to be about 1.059 points away from my sample mean of 5.3. And if I look at my data, That number makes sense, so I'm feeling pretty good about it. Now that's different from what we're about to calculate, the standard error, right? So the standard deviation, or S, tells us the spread, the typical spread of scores in our sample. But in order to calculate T, we need to know the expected spread of sample means of a sample size of n equals 10 from this population. So that's what we're going to calculate now. So for this bottom version of the formula using the variance, I can just plug in that 1.122, and then I end up with the square root of, let's see, so you just kind of scoot the decimal place 1 to the left because you're dividing by 10. You get 0.112, rounding to the thousandths place. And the square root of 0.112 is 0.335. There you go. Now let's use the version of the standard error formula that uses the standard deviation instead of the variance. And think about why these two are equivalent, right? So for both of these, you're taking the square root of the sample size at a certain point, right? But for this one, there is no square root in the numerator because the square root of the variance is the standard deviation. So that square root has already happened here, but it still needs to take place in the numerator. All right, so now let's plug in our standard deviation that we found. So this 1.059. So we end up with 1.059 divided by the square root of 10, which is 3.162. And our final answer is the same as the other way to calculate it. 0.335 is our standard error. Now, please don't feel inclined to do both versions of the calculation. Whichever one you're more comfortable with is fine with me. I'm more comfortable with the one using the standard deviation because I like to look at my standard deviation and see if it makes sense based on the scores in my sample. But it's up to you. So now we take all of these calculations that we found that lead up to our t-statistic up here at the top. So we finally have our denominator, right? Our standard error. And our standard error, no matter which way you calculate it, is 0.335. So now we can compare that actual difference between our sample mean and our population mean of 1.3 to the difference we would expect to see even if exercise had no effect on sleep quality. And we find that when we calculate our t-statistic, we get 3.881. So this tells me that the observed difference in sleep quality between our sample of exercisers, we can call them, or males over 35 who exercise regularly. Let's shorten it to exercisers. That's my funky E there. So observed difference in sleep quality between our sample of exercisers and the population is 3.881 times larger than the difference expected due to chance. Or in other words, the difference expected even if exercise has no impact on sleep quality. All right. Just helping you understand what that t-statistic tells me. So now the question is, when we get back to the hypothesis testing part of this, if my alpha level is 0.05, is there less than a 5% chance that I would get this sample mean of 5.3 from this population just due to chance, even if exercise has no impact on sleep quality? And to answer that question, we need to compare this 3.881 that we calculated to our critical value. And that 3.881 exceeds our critical value. So we know that there's less than a 5% chance of getting a sample mean of whatever we got. What was it? Of 5.3 from this population if there was no effect between exercising and sleep quality. So for step 4, our decision is to reject the null hypothesis. And we could just state that, let's see, let's be specific. So results suggest, right? Always kind of try to say that so that you recognize that this isn't the end-all be-all. Results suggest men older than 35 who exercise regularly get significantly better sleep. So we have our independent variable, exercising regularly, our dependent variable, getting sleep, right? And the fact that it's a one-tailed test, better sleep. And we also have the fact that it's a significant finding. So I hope that this example helps give you a refresher on how to calculate the mean and standard deviation using raw data from a sample, and additional practice doing a t-test for single samples.